In this module, we discuss the kinetics of first-order reactions. Continuing with our exploration of rate laws, we now turn to first-order reactions. For a first-order reaction of reactant A to products, the rate is directly proportional to the concentration of the reactant A, denoted as C. The rate law for such a reaction is given by V equals K times C. If we assume that the stoichiometric coefficient of A in the reaction is 1, the reaction rate is equal to the negative derivative of C with respect to time. Combining these equations, we obtain a differential equation that describes how the reactant concentration C changes over time. To solve this, we separate the variables and integrate both sides of the equation. On the left side of the equation, we integrate dC over C from C0 to the value at any time C. Here, C0 denotes the initial concentration of the reactant at the reaction start. On the right side of the equation, we integrate K by T from time 0 to the time T. The integral on the left side of the equation produces an expression natural logarithm of C over C0, which is equal to minus KT. With some rearrangements, we obtain the integrated rate law for a first-order reaction. C as a function of time is equal to the initial concentration C0 times the exponent of minus KT. In a first-order reaction, the concentration of the reactant decreases exponentially over time, a behavior described by the integrated rate law. This relationship is depicted here graphically, where the concentration of the reactant is plotted against time. The resulting curves, which are derived from the integrated rate law equation, clearly show that the rate at which the reactant concentration diminishes is dependent on the rate constant K. The curves illustrate that a larger rate constant corresponds to a faster exponential decay of the reactant concentration. This exponential decay is a distinct characteristic of first-order kinetics. For a first-order reaction, the natural logarithm of the reactant concentration plotted against time yields a linear relationship. This linear dependence is derived from the integrated rate law by taking the natural logarithm of both sides, resulting in this equation. It indicates that a graph of the natural logarithm of concentration versus time will produce a straight line with a slope of minus k and an intercept equal to the natural logarithm of initial concentration. This figure provides examples of linearized concentration-time relationships for first-order reaction kinetics. In this plot, a larger rate constant corresponds to a more negative slope of the linearized reactant concentration. This approach is known as linearization of an equation. Linearization is the transformation of nonlinear relationships into linear ones, making it easier to analyze and interpret experimental data in comparison to theoretical models. By plotting the natural logarithm of the reactant concentration against time, we obtain a straight line that simplifies the complex kinetics into a visually comprehensible format. This linear plot can be useful for determining the rate constant of a reaction and, if necessary, the initial concentration of reactant from experimental results. The half-life is the time required for the concentration of a reactant to decrease to half of its initial value. The half-life for a first-order reaction can be derived from the integrated rate law. By setting the concentration at half-time to half of the initial concentration C0, we can express the half-life as the natural log of 2 divided by the rate constant K. This equation reveals that for a first-order reaction, the half-life is inversely proportional to the rate constant. In other words, the higher the rate constant is, the less time it takes to consume half of the initial amount of reactant. Furthermore, the half-life is characterized by its independence from the initial concentration. This is a unique feature of first-order reactions kinetics, distinguishing it from other reaction orders where the half-life varies with concentration.